We will now move on to talk about acceleration time graph and acceleration time equation. Again, similar to the discussion of velocity time equation and graph, we'll be relating our acceleration time equation and graph to the first two topics that we have discussed, which is on displacement and velocity. We relate between displacement, velocity, and acceleration together in this discussion over here. So let's try this out. So we'll again use the oscillation that is most common to us, which is from the equilibrium position, moving towards the positive maximum displacement, then continue its oscillation. So it'll be something like this. Okay, move towards the positive maximum displacement, then continue its oscillation. So if this is the oscillation that is happening, then our graph will be something like this. And this is a sine curve. Therefore, we know our equation to relate between displacement and time will be x equals to a sine omega t. So this is the equation. And we also know that if we differentiate this equation that relates between x and t, we'll obtain our x component of velocity, which is vx. And we differentiate this equation, and the answer of our differentiation will be a omega cos omega t. So this will be the velocity of this object undergoing simple harmonic motion. It will be varying in a cosine fashion as time passes. Okay, so this is sine. So for velocity, it will be in a cosine graph, but this is not shown in this slide over here. Okay, so now we'll try to draw, or we'll try to plot our graph, our acceleration time graph. And how we do it is we'll again focus on a few specific moments that are interesting to be investigated. And these are the 5 points that are interesting to be investigated, because these 5 points here represents moment in which the object is at its equilibrium. So x is equals to 0 at these 5 moments here. So why are these 5 moments here interesting to be investigated? Because when the object is at the equilibrium position, the spring is not stretched. At the same time, the spring is not compressed. So the spring is at its equilibrium length, or its original length. So when that is the case, when the spring is not compressed, when the spring is not stretched, you should expect 0 restoring force due to the spring. Okay, so spring is not stretched and compressed when x is equal to 0. Therefore, you should expect no restoring force, because there's no stretch, no compression. And because there is no force, you learn from the video on that relates between force and acceleration. You learn that if F is equal to 0, if the restoring force of a spring is equal to 0, then the acceleration will be equal to 0. So for these 5 different moments here, you should expect the acceleration for these 5 moments to be 0 as well. So if you draw a line over here, you should expect for your acceleration time graph, these 5 moments here will return acceleration equals to 0. Okay, but now what we are going to continue to do is we'll continue to determine whether the graph should be above the time axis or below the time axis for this time interval between the red dots. We'll try to determine whether it's up, down, up, or down, up, down, up, down. Okay, we'll try to do that. And how we'll do this is we'll focus it section by section. So let's focus on the first section, in which the block moved from x equals 0 to x equals to plus a. Okay, so when the block moved from x equals 0 to x equals to plus a, you should expect the object to be moving in the positive direction. And because it's moving in the positive direction, the Vx is positive. This is what we have discussed in the velocity section just now. Okay, but the next thing I want to discuss about is whether the speed increases or decreases when the object is moving from the equilibrium position to the maximum displacement over here. Okay, when the object is moving from here to here, is it slowing down or is it speeding up? Well, remember over here, when you reach this point over here, the velocity should be equal to 0, because you need to make a change in direction. So the velocity here is 0. That means you have to slow down. When you reach this point, only you can enter 0, right? If you speed up, how do you stop here? You have to slow down, only you can stop here. Therefore, we know that the object is actually slowing down while it is moving towards x equals to plus a. A general tips that we can use to determine whether it's speed up or slow down is, If it's moving further away from the equilibrium position, it must be slowing down. And if it's moving towards the equilibrium position, then it must be speeding up. And in this case, this object here is moving further away from the equilibrium position. It's going away from the equilibrium position. Therefore, it must be slowing down. So if the object is slowing down, we learn from chapter 2, kinematics of linear motion, that the acceleration and the velocity must have opposite sign if it's slowing down. So ax and vx should have opposite sign. Then if you know vx is positive and you know ax is opposite sign of vx, then you know ax must be negative, because ax and vx must be opposite in sign. If vx is positive, then ax is negative. So for this section here from T0 to T2, you should expect your graph to be plotted below the time axis, somewhere around here. So this is for the first section. Next, we move on to the second section, in which the object moves from positive A towards the equilibrium position. So the object is moving from here towards here. Okay, over here towards here. Yes, something like this. So the motion from here towards here, it's in the negative direction. So if the object is moving in the negative direction, you should expect Vx to be negative, because it's moving to the left. Left is the negative direction. Vx is negative. Then we also know that the object is now moving towards the equilibrium. It's moving towards the equilibrium, so it must be speeding up. So if the object speeds up, then we know that the acceleration and the velocity should have the same sign. So if velocity is negative, acceleration should also be negative. They both should have the same sign because the object is speeding up. Therefore, you know that ax is negative for T2 until T4. Therefore, we should expect our graph to be plotted below the time axis from T2 to T4. Okay, let's continue. For the third section, which is from T4 to T6, our object is moving from x equals to 0, the equilibrium position, to x equals to negative a. So it's somewhere starting from here towards here. Okay, so the object is moving in the negative direction. It's moving to the left, so it's moving in the negative direction. Therefore, you should expect Vx to be negative. But at the same time, you can see that this object here is moving away from the equilibrium position. Moving towards x equals to negative a, it's moving away from the equilibrium position. And if it's moving away from the equilibrium position, it must be slowing down, because you need to stop over here, only you can make a change in direction. So if you want to stop, you have to slow down when you move towards here. So if it's slowing down, you know that A and V should have opposite sign. So if A and V have opposite sign, if V is negative, A must be positive. So therefore, from T4 until T6, you should expect the acceleration to be plotted above the time axis, somewhere around here. Okay, then next, the fourth section is over here. For this fourth section over here, you'll be moving from x equals to negative a to x equals to 0. So it will be somewhere from here towards here. Okay, so the motion is towards the positive direction. It's moving to the right. So it's moving to the right positive direction. Vx should be positive. At the same time, this object here is moving towards the equilibrium. It's moving towards the equilibrium, therefore it must be speeding up. So if it's speeding up, you know that the A and the V must have the same sign. So if V is positive, A should be positive as well. Therefore, you should expect the plot from T6 to T8 to be above the time axis, somewhere around here. Okay, I can continue to go from T8 to T10, T10 to T12, T12 to T14, T14 to T16. But you see it's the same pattern again and again, because this is the second oscillation and it's the same thing as the first oscillation. So you should expect the pattern will follow as time passes. Okay, so now if you know that the graph should be down, up, and you know that at these red dots over here, you have to have 0 acceleration at these moments, then if you use your logical deduction, you will know that the graph should look something like this. So if this is the shape of the acceleration time graph, you can see that this is a negative sign, because a normal sign will be something like this, and this is flipped vertically. That's why it's a negative sine curve, Therefore, your acceleration equation should be negative sign. Okay, but now you don't know what should you fill in here because you don't know what value should you put over here. I believe you know it's not a, because just now we know that for velocity is a omega, so it must be something different over here for the maximum in the positive direction and the maximum in the negative direction. So let's try to determine that. But how do we determine it? Again, using differentiation. So we know from chapter 2 that acceleration is dv against dt. So we are going to do the same thing, but now we are going to differentiate velocity. Previously, we differentiate the x equation. Now we differentiate the v equation. So if you differentiate it, now a and omega is constant. Your oscillation doesn't become faster with time. The oscillation doesn't become slower. So the omega is constant. The omega is constant. The amplitude is also constant because the amplitude doesn't change to become smaller, doesn't increase with time. So a and omega are both constant, so you can bring it out. So it becomes a omega d cos omega t against dt. So now you know that in order to differentiate this, you have to use chain rule. You have to break it from dy dx to dy dA, dA dx. So if you break it, it will become a omega, just bring it here, then it will be d cos omega t divided by d omega t. Okay, this is dA, so copy dA over here against dx, so dx here is dt. Okay, so if you differentiate cos differentiate will become negative sign. So what happens here will be negative sign, and what happens at the last block of differentiation will be omega. And now if you rearrange it, you see that if you put sine omega at the back and negative in front, what you should put in the middle over here should be a omega square, because it's omega times omega. So what you should put here is a omega square, and because you know this is negative sine graph, so what you should put at this point and this point over here will be positive a omega square and negative a omega square. So a omega square will be the maximum acceleration that can be achieved, and negative a omega square will be the maximum acceleration that can be achieved in the negative direction. Okay, so this is positive direction, this is negative direction, so this is the maximum you can achieve. Okay, so again, this equation is not fixed. If your oscillation follow a cosine curve, then it'll be a different equation for acceleration, and let's do that. So now let's say our graph is a cos omega t. So let's say we start from the a amplitude and oscillate towards the equilibrium position, then continue our oscillation like this. Then we know that x is different, of course v will be different, and indeed v is having a different equation right now. So let's try to differentiate this equation for v to determine our equation for a. So let's substitute in again, these 4 points here, the acceleration should be 0 because there is no stretch, no compression at these 4 points. Okay, if you substitute in negative a omega sine omega t inside, you can bring out the negative a omega because these are constants. Now we want to differentiate sine omega t, you have to break it using chain rule. So it becomes sine omega t divided by omega t dt. Okay, so for this part, sine differentiate become cos, and omega t differentiate, you get omega. So now if you rearrange your equation, you will see that ax is equals to negative a omega square cosine omega t. So you should expect this graph over here to be having a negative cosine shape. So it's a vertical flip of this graph over here. This is a positive cos, right? So if you flip it vertically, then you get a negative cos. So this is negative cos, and what you fill in for the maximum, in the positive direction, it will be a omega square positive. In the negative direction, the maximum is negative a omega square. Okay, so this is the equation, and this is the graph for acceleration if our oscillation follows a cosine pattern. Okay, so now I put it side by side for comparison. You can see that if our oscillation starts at different point, if it starts at equilibrium and it moves towards the positive direction first, then it's a sine curve. Then your acceleration will also be a sine curve, but now it's negative. Okay, but if your oscillation starts from the positive maximum displacement, then it will be a cosine graph. Then for this oscillation, our acceleration will be a cosine graph, but again, it's negative. So you can see here the sign has been changed, but the shape is still sine, it's still cos, but you change from positive to negative. Okay, so one of the main point I want to carry that I want to deliver here is that there's no fixed equation to relate between x and t, v and t, and a and t. It all depends on how the object starts oscillating, whether it starts from the equilibrium position or it starts from the amplitude. Again, to determine the actual equation, you have to go through the differentiation process yourself. You cannot say, oh, acceleration must be sine or acceleration must be cos. No, you have to do the differentiation. From x, you differentiate to get v. From v, you differentiate to get a. That's how you obtain the equation to relate between acceleration and time. The second important point that I want to deliver is here. Okay, so if you look here, if I make some rearrangement to these two equations over here, something like this, see carefully what I change over here at these 2 points. Now, if I rearrange my terms like this, now you can see that what's at the back over here, a sine omega t, is just x. And you can see here what's at the back here, a cos omega t, is also just x. So for your acceleration equation, you will always see that acceleration is equals to negative omega square x. This is for sure. Okay, this one, it's true no matter how you start the oscillation. You start the oscillation at the equilibrium position, it will still obey a equals to negative omega square x. You start at the amplitude, the positive side or the negative side, you still get a equals to negative omega square x. This one must be obeyed. Therefore, the second point I want to deliver is that all simple harmonic motion must obey ax equals to negative omega square x. Of course, when I say must, it's a bit too restrictive because it can be ay equals to negative omega square y, or it can be az equals to negative omega square z. Okay, but what I'm saying is that the relationship here must be obeyed, in which the acceleration is directly proportional to the displacement and they have opposite sign. Okay, this is the relationship and this relationship must be obeyed. Okay, so this is the criteria. We can think of it as a criteria they discussed earlier. And usually if you read in books, right, they call this thing as the hallmark for simple harmonic motion. Why do they call it as hallmark of simple harmonic motion? Is because if your motion obeys this equation over here, right, then basically all three criteria that we discussed earlier in the previous section will be obeyed. If your motion obeys this hallmark of SHM, you see that the force and the displacement must be in opposite direction. You see criteria 1 be achieved. You see that the force is directly proportional to the displacement. You see criteria 2 being achieved. And you see that the acceleration and the displacement must be in opposite direction. Criteria 3 will be achieved. All three criteria will be achieved if your simple harmonic motion obeys this equation. If your motion obeys this equation, all three criteria that we discussed earlier will be achieved. That's why this equation is important and call it by the name the hallmark of simple harmonic motion, or it's the equation that represents simple harmonic motion. That's why they call it hallmark. Okay, so that's a little bit of discussion for how to relate between acceleration and time using graph and equation.